Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture 41 of module 9, and this is related to the diffusion based coatings mostly in the solid state. So this is a protective measure to protect the surface from or the component from various aggressive attacks, corrosion, high temperature oxidation, even to some extent wear and erosion at high temperature and so on. So if you look at this particular component here, so basically this is the pipeline, and as we all know, when we actually transport petroleum, either for transportation from one place to another or in a refinery which actually is subjected to various kinds of distillation process at high temperature. So in such cases, when we transport crude oil and at elevated temperature, the medium becomes extremely corrosive. So the pipes which are made out of steel or various kinds of alloy steels, they do undergo various forms of degradation, and one of the most prevalent and dangerous form of degradation is such formation of pits and coagulation of these pits or expansion of these pits to create a big hole like this. And of course, this is the hole which is absolutely undesirable because it leads to catastrophic loss of petroleum or the carrying gas, whatever is being conducted. And the entire system has to undergo a shutdown, and this repair requires a lot of time and effort. And if one actually goes through the failure analysis of these failed parts, then one comes out with various forms of degradation, including formation of corrosion products, rendering the entire steel pipeline or the surface of the pipe entirely brittle and converted to oxides or some other compounds. A similar thing is also encountered in thermal power plants. For example, when you conduct the superheated steam through the superheated tubes from the boiler to before actually it's projected onto the turbine. So there we are talking about not only high temperature, we are also talking about high pressure. So combination of high temperature and high pressure can lead to creep damage, but more often and before even creep can begin, what is quite common is oxidation and oxidation of the layer at the surface, and the oxide layer gradually penetrating inside in the form of, so that renders the steel surface fairly brittle, and it cannot take load anymore. So inside pressure tries to bulge the tube, and in the process the stress when it crosses the tensile limit, the tensile strength limit, it actually can lead to creation of a crack, and the crack propagates, and that leads to such an elongated failure. So bulging is not so dangerous because this is just the indication of that the failure might happen, and usually these kind of degradation initiates at the joints or at areas where, because of manufacturing defects or some other reasons, maybe bend regions and so on, the thickness of the shell is thinner. So bulging may happen there, and when the pipe starts bulging, the thickness of the layer decreases, and then formation of such crack becomes quite possible. So by all means this needs to be avoided or prevented. So either the crack happens over a period of time or catastrophically, it is certainly not desirable and needs to be prevented. Now, one of the major approach of prevention of such failures is through diffusional treatments. Now, here we basically want to strengthen the substrate material, the tubes or pipes or even heat exchanger surfaces with certain amount of elements, certain typically elements like aluminum, silicon, and chromium. So these are the three sort of magic elements which are often used primarily because of the fact that the oxides of these elements are fairly stable, non-volatile, and actually can act as a preventive layer or barrier layer against further propagation of further oxidation. So diffusion coating, as the name suggests, is a process of enrichment of the surface with regard to one of these elements, so that the surface is now alloyed with these elements, and when the component is exposed to high temperature or fairly corrosive environment, aggressive environment, then depending on which of these elements are present in atomic form, these elements now can react with oxygen and form an oxide layer. So typically this aluminum coating is one of the most common approach for such protection measures. So applied on steel for high temperature applications. It also gives us typical lustrous appearance. Apart from very high temperature components, even medium temperature components exposed to fairly corrosive gaseous attack could be the automobile exhaust pipes or exhaust regions, where such coatings are routinely applied. Now, apart from diffusion coating, one could also go for conversion coating, which essentially is a reaction layer produced by certain reactions with certain elements or certain salts that are applied on the surface, again for oxidation protection primarily. One can go for thermal coatings or thermal barrier coatings by, say, flame spraying, or metal coatings using electrochemical or electroless processes. One can go for diffusion measures, one can go for deposition measures from the vapor state, and one can also go for organic coatings, primarily when the application is not for high temperature. So such important components, the parts of a bigger machinery, needs to be protected when you actually expect combination of high temperature, aggressive environment, and with or without mechanical interaction. The whole process, as I said, is diffusion based. So essentially one has to understand that the thickness that we form, typically if that is the layer, so if this is the component surface and this is how we are introducing the element, be it silicon or chromium or aluminum. So from this surface region, these diffusants enter and go up to a certain depth. The depth up to which such diffusion occurs, if that is x, then this x is proportional to the root over of t. And the proportionality constant k in turn is actually proportional to the diffusion coefficient. So this is why we have to understand that temperature has a very major role to play here. Higher the temperature, higher the diffusion coefficient, and hence higher the value of k, and as a result, for the same period of time for isochronal treatment, the diffusion depth will be higher. Or in other words, for the same amount of time that we spend, if the temperature is higher, the thickness of the coating is deeper. So this is how roughly one can design a typical experiment in terms of time temperature combination and decide what should be the thickness of the diffused layer or the protective layer. So diffusion, as we know, is as we all know, is a typically thermally activated process. So we imagine that we have a crystalline matrix, but there's no necessity it has to be crystalline. Even in non-crystalline matrix, if there is a concentration gradient, we generally expect the solute to diffuse down the concentration gradient. So typically, if this is the concentration profile that we talk about, and to begin with, if we are talking about a diffusion couple, which let's say on one side is copper and on the other side is nickel, then we would expect nickel to diffuse towards copper and copper to diffuse towards nickel, provided they are mutually soluble in each other. And as a function of distance or as a function of time in an isothermal condition, initially the concentration profile will be sharp. So on this part we'll have 100% copper, on this side we'll have 100% nickel, but over a period of time we will tend to see certain diffusional profiles following like this. And at a particular time temperature combination, typically copper concentration as a function of distance will look like this, and nickel concentration on the other hand will look like this. What it means is that to begin with, we had a sharp interface. Over a period of time, this interface gets diffused. And this is purely because of the diffusional phenomenon. And we all know that there could be two kinds of diffusional process. One is the so-called steady state, where concentration profile or the concentration profile does not change with time. So we are talking about maintaining the same concentration gradient like here, and then the flux of course will be proportional to the concentration gradient, and the proportionality constant is the so-called diffusion coefficient. But in reality, when we actually go for industrial practices, then obviously the concentration profile or the concentration gradient that we are talking about need not remain exactly the same throughout the experiment. So if this is the component which is subjected to the diffusional environment, or an environment which has certain diffusion potential, solute concentration, then beyond a certain period of time or after a certain period of time, we expect that this surface region from all sides to get enriched with the solute atoms. But if we begin with a certain concentration, this concentration need not remain constant over a period of time at the same temperature, or if we vary the temperature. So in such case, we are talking about the non-steady state diffusion, where the concentration varies with time, and we invoke the fixed second law. And fixed second law basically is an extension of the first law, or the expression of the first law like here, and essentially it boils down to exactly this expression, where now we are saying that the concentration as a function of time. So earlier we said concentration as a function of distance, and now we are saying concentration as a function of time is proportional to the second derivative of the concentration profile. And the proportionality constant of course remains the diffusion coefficient. So typically an approximate solution using the error function approach could be like this, where we see that the concentration difference is again proportional to the time, the square of time, and this is very similar to the earlier expression that we have seen before. So this x will be again proportional to root over of t for the same isothermal condition. Now there's one other important thing to be mentioned, that in all along we have been referring concentration as a guideline for diffusion, and we mentioned that concentration diffusion always occurs down the concentration gradient. But this is typically true in cases where for example delta H, the enthalpy of mixing, is 0 and the solution behaves as ideal. So there's no problem, concentration always, diffusion always will occur down the concentration gradient. But when delta H is negative, then also there is no problem. But when delta H is positive, in the rare case which refers to typically the Gibbs energy variation as a function of composition, which shows sort of the immiscibility dome, which is purely because of delta H as positive. In such cases, diffusion in the immiscibility zone may appear to be occurring up the concentration gradient, which is typically called uphill diffusion. But whether it is delta H 0, positive, negative, whether it is downhill or uphill diffusion, in all the cases, the cardinal rule remains that diffusion always occurs down the activity coefficient or down the chemical potential gradient. So from higher chemical potential to lower chemical potential. And there is no contradiction or any confusion with regards to this particular principle. Now, how do we do the process? So we need a muffle furnace, typically a covered region where we can maintain isothermal condition. Ideally, we first should evacuate, and if we can evacuate, then we can hold slightly at a lower temperature. But typically, I would say not necessarily 850 or to 1600, this is on the higher side, but one would typically look at 700 to about 1000 degrees centigrade is the typical temperature range in which diffusion processes occur. I already mentioned that typically these are the aluminum, chromium, silicon are the three magic elements, but zinc, titanium, some of the other elements which also have very high affinity for oxygen can equally be useful for diffusion coating preparation. So we generally will choose an element which actually has high vapor pressure, higher than the base substrate, so that it actually can vaporize easily and remain in the vapor state and maintain certain activity or concentration. So this powder, usually you pack the component inside a bed, and that's where the name pack cementation or pack coating comes from. So these powders actually are made to react. They should have the property of undergoing a sublimation process. So they react, they go into the vapor state, and then they decompose, and when they decompose typically on the component surface. So if I pack with powders, the powders go into the vapor phase, and then from the vapor phase they come in contact with the component surface, and that's where they decompose and then liberate typically the target elements in the nascent form or in active carbon form. So active atomic form. So these atoms, the nascent or atomic species, now are ready to get adsorbed and diffuse and get dissolved. So this diffusional process is preceded by the reaction of the gaseous chemical compounds, typically metal halides, which go into the vapor state and then sublime on top of the component and then liberate the elements of interest. This can be there could be also an equivalent process where one can try out with the liquid bath, but that is what we'll discuss later. As I said, this is the typical temperature range, or it could be just about 700 to 1000 degree, 1100 degrees centigrade, depending on, of course, which component, what is the thickness that we desire, and how much time we can afford to expose to chances of oxidation and so on. So we could go for, let's say, chromium coating, and in that case we say chrome colorization or chromium titanium coating, chromium nickel coating, and so on. Typically the diffusion thickness will be about 10 micrometer to about a few millimeters, and this thickness typically depends upon the time temperature combination and of course the potential of the environment that we create from which diffusion occurs. So the process generically is called pack cementation. So in this we have and the primary objective is to improve the oxidation resistance. So as I already mentioned, these are the three magic elements: aluminum, chromium, and silicon. They are so-called magic elements because they actually not only form very they very readily form oxides, but these oxides actually lie fairly low in the Illingham's diagram, or in other words, they are fairly stable and adherent oxides, and that's how they provide the protection. So say for example, if we are interested in providing aluminum to the surface, so we will go for a process whereby aluminum will be made to react with an halide compound, sodium fluoride, so that it forms aluminum fluoride, which is a relatively unstable compound. So this aluminum fluoride then reaches the steel substrate surface, gets decomposed and deposits aluminum. So this aluminum is in the nascent state, and hence this aluminum can now readily diffuse in. And aluminum, as it diffuses, it also, depending on the solubility condition, can react and form intermediate compounds like iron aluminides of various forms. But nevertheless, they make the surface richer in aluminum, and that aluminum protects the steel or the certain other alloys. It is not necessarily steel or ferrous alloys. These kind of processes are also routinely used for substrates or alloys based on cobalt, nickel, even titanium, and so on. So this diffusion process continues until aluminum potential is high in the environment, or in other words, deposition of aluminum and concentration of aluminum on the surface is high. And as I already mentioned, this is a typical temperature range, which actually the process can run for several hours, even beyond 10 hours, maybe 15, 16 hours, 20 hours, depending on what thickness we are desiring to. So this is basically the process of back cementation, and in some cases, as it's shown here, it actually can lead to either formation of a solid solution or a solid solution. That means say aluminum dissolved in iron, but when the concentration goes beyond a certain threshold value, then it actually can form, instead of iron, aluminum dissolved in aluminum. This can also now form aluminides like Fe3Al or FeAl and so on. So obviously the surface will be richest in aluminum, so the aluminides will be mostly confined to the surface region, and below that will be such solid solution. So when it is aluminum, and we are not talking about a generic system, we are talking about aluminum diffusion, it can be through aluminum or aluminum alloy, then the process is called aluminizing. So the target, of course, is to improve the either atmospheric corrosion resistance or high temperature oxidation resistance. So this is also a process which at times is considered competitor to galvanized zinc coating, and this is more effective than zinc coating at elevated temperature. At room temperature, of course, the process is not as competitive as zinc coating, which because of certain process advantages appears to be more cost competitive. So we produce a sacrificial layer when we when we actually subject this component after coating to a corrosion environment, and steel in that case will be the cathode. So we'll get protected by way of oxidation or degradation of aluminum or zinc on the surface. So as I said, for high temperature application, of course, aluminum coated steel is more cost effective. So we actually, the various methods which are possible for diffusion of zinc or making the surface richer in aluminum or zinc or like that could be many of them are possible. It's not that only solid state back cementation or aluminizing is the only process. It can be typically a solid state diffusion process like we were discussing so far, also including pack cementation, calorizing, hot dip coating, rolled in coating, spray coatings and so on. But for the time being, we are talking about only the solid state process wherein the nascent atoms get adsorbed at the surface and then move. It's very similar to carburizing, nitriding processes, but the only difference here is that we are talking about entirely solid state diffusion of substitutional atoms. So all these so-called magic elements that we are talking about, aluminum, silicon or chromium, they all are substitutional elements in steel matrix. So if you, following the diffusional process, the coating is created. If you look at, so we are now seeing something like about half a millimeter or 0.2, 0.3, up to about 0.5 millimeter thick coatings, and these coatings basically, so we have a top layer. If you just look at the surface, there's no etching here because this is primarily an Fe3Al layer, highly protective, highly corrosion resistant aluminide rich layer, iron aluminide rich layer. Then we'll have a diffusional zone or the composition. Actually, the important thing to note here is that if we plot concentration of, say, aluminum as a function of distance from the surface, then we see a profile like this. And this kind of gradually decreasing or a diffusional profile or a diffused profile is purely because of the fact that it's a diffusional process. So obviously, the concentration is very high, at the highest at the surface region. So this is the region which will have all the aluminides, and below that we'll have solid solution and aluminides both present. So from the top it will look like this, where we have these aluminides which are essentially faceted phases. In other words, phases which are not polygonal like this, with curved boundaries, but will appear as phases with some sharp interfaces, sharp boundaries, which is also flat and which is reflective of the fact that these are intermetallic phases with high interfacial energy. The next element that we should talk about now, before we move to the next element, let's also say that calorizing is another term which we often see in the literature. We have to know that this is basically a patented process. So that's where the name comes from. Nothing but ideally it's a diffusional process of enrichment of aluminum, and it was patented initially in the USA and was highly utilized, and even today it's one of the most effective methods for iron, cobalt, nickel base alloys, particularly the superalloys. The turbine blades, the vanes and discs and so on are routinely provided with these kind of coatings. Of course, zirconium is another material which is also very highly used. So the aims typically would be high temperature oxidation resistance, abrasion and erosion resistance, even carburization resistance. You don't want carbon to be lost by diffusion. Resistance to stress corrosion, cracking, resistance to erosion and corrosion in the presence of molten metals or non-metals like gaseous environment. The next element is silicon, other than aluminum, what we are talking about. It's a very similar process. Here also we are looking at liberation of nascent silicon onto the surface so that silicon can diffuse in. So we use it, we actually pack it with silicon containing materials, typically silicon carbide, and subject to a temperature in excess of 1000 degree or around 1000 degree, and then we charge silicon tetrachloride. So this silicon tetrachloride basically at that high temperature has a tendency of cracking and liberating. So silicon goes out. The silicon now is liberated as a silicon atomic form or nascent form, and that silicon gets adsorbed to the surface and diffuses in. So we can go up to about a millimeter or 2 millimeter kind of a thickness, depending on, of course, time and temperature combination. One can apply this for low carbon steel or alloy steel and go to a silicon content as high as 10, 12, 13% or so. So silicon coated or siliconized steel has very high corrosion resistance and also oxidation resistance, and gives a fairly high hardness onto the surface because of the formation of, here again you are talking about not only formation of iron with silicon, or typically iron substitution or solid solution of silicon in iron. This is of course possible, but in addition you can also form certain silicides, for example FeSi2 and so on and so forth. The other element which is in the same series is very important is chromium. Chromium also has a similar tendency of formation of Cr2O3. So typically when you enrich with aluminum, so aluminum protects by formation of alumina, Al2O3. Silicon is prone to formation, or the most stable compound is silicon dioxide, and in case of chromium again you are likely to form Cr2O3, not CrO3. So this trivalent compound, trivalent oxide compound, is fairly stable and has low vapor pressure, so it doesn't evaporate, and protects the steel or any other alloy to a large extent. So this is the typical temperature, and the carrier gas here, or the gas which actually helps us in liberating chromium, is a chromous oxide. So all these are basically, be it aluminum fluoride or silicon tetrachloride or chromous iodide, they are all essentially halide compounds, and so this is very similar to the chemical vapor deposition process. But the difference here is that in CVD, PVD or such process, we will also learn later, the typical diffusion profile will be sharp. So this is the coating region and this is the substrate region. So typically the interface is sharp. Whereas in all such diffusional processes, we expect a shallow diffusional profile. And this happens because of diffusion ingress of the elements that we deposit onto the surface as a function of time and temperature. Another process before we end actually also is a diffusion based process, but fairly different type, is called roll bonding. In fact, it's also called so-called accumulative roll bonding. And essentially, if you do it only once, you call it just roll bonding. If you do it multiple times with multiple sheets, then you call accumulative roll bonding. So let's say these are the protective layers, and these are the two layers, two sheets that you want to protect. So you first place one upon the other and create a pack like this, and then you subject this pack, this sandwich of A, B, A, B, A, B kind of layers to pass through a roll. And when it passes through the roll, then obviously you are reducing the thickness, and when you reduce the thickness, there is elongation, and in the process there is a mechanical driven interdiffusion at the interfaces. So this blue and red undergo diffusional intermixing at the interface because of this pressure, compressive pressure applied by the rolls from the two sides. And in the process we form a layer which now, so earlier we had layer A and layer B, and after diffusion, when the thickness reduces, then the length increases and the thickness reduces, and in the process the interface gets diffusional bonded. Now this is very useful for applications where we are dealing with large surface area, say big sheets, which could be typically used for heat exchanger applications, refrigerators, or maybe even carburetors, where we are talking about large surface area and of thin sections. So when you subject a thin section to diffusional bonding processes, then there is every possibility there will be surface corrugation or complete penetration, through and through penetration. So in the process, the thin sheet can be rendered fairly brittle, which we don't want. So in such cases, we actually do such roll bonding processes so that there is enough strength at the interface because of mechanical interdiffusion, but we also create very good surface protection. And these are typically the orientation image mapping of the kind of structures that one develops. We see ultrafine grains, and these different colors actually refer to solid solutions but in different orientations, which means that subsequently after diffusion, after rolling, we also subject to higher temperatures, so the deformed structure gets recrystallized, and then we see such recrystallization texture happening onto the surface. So we end up here just to remind you that we need to understand what is pack cementation, what is the role of diffusion in it, and what is the driving force for diffusion, what is the difference between steady state and non-steady state diffusional processes, what is the difference between calorizing and hot dip aluminizing. We haven't talked about yet hot dip processes. What is role of non-steady state diffusional process in pack cementation. Then why is vaporization absolutely essential in all solid state coating processes, diffusional processes. Which way do they differ from each other, aluminizing, chromizing, siliconizing? So what is there common in them, and what is the difference? I mean, all of them are primarily meant for surface protection against high temperature oxidation, and all of them produce diffusional treatment of substitutional type. In some cases, they remain only a solid solution. In some cases, they form intermetallic phases, and they are usually batch processes because of the very nature of creating a pack and subject diffusion and then withdrawing and so on. So vapor pressure does play a role because the diffusant has to go to the vapor state, and one has to find out what are the typical engineering components which are routinely subjected to such diffusional treatments. Roll bonding is a very special process. We have to know where is it applicable and why. Why can't we do normal pack cementation or diffusional treatment? Why do we go for roll bonding? What are the process parameters and so on? So we'll end up here. Thank you very much.